So hello everyone. So thanks for waiting just before the lunch. I know you might be hungry because I am also. So, so I am Jayesh Goyal. I'm a PhD student in astrophysics, as I was introduced earlier. Thanks for introducing. And like today I'm going to take you the journey of exoplanets, like how wonderful they are, and and the most important thing we study these planets are because like we just want to know what is out there, what kind of planets does nature make. And we have always been surprised by this thing. And the most important question that we want to answer is, are we alone in this universe? Like everyone is like excited by this question, and I am also excited by this question. So that's my motivation to study exoplanets. So let's start that journey now. So first is, what is an exoplanet? So you can see here, this is our solar system. So like if you go outside in the day, you can see the sun, but we fail to realize, like UK might be an exception, but we fail to realize that sun is basically a star. Sun is a star. Mercury, Venus, Earth, Jupiter, all are the planets in our solar system. So Sun is a star. We have our own system of planets. Similarly, if you go at a night sky and see the stars, you might think that those stars also might have planets. And like humans have been thinking about this for last like 1,000, 2,000 years, but we have never been able to like safe, truthfully, like to find like whether those stars have planets, because we never had the technology to do that. But recently we have been able to do that, and this is what I will talk about. So basically, exoplanets are planets around other stars. So you can see this is our solar system, and this is a similar planetary system called Kepler-11 system, where they have their own star and a system of planets. So fundamentally, exoplanets are planets around other stars. Now as we understand this, let's come back to our own solar system, and I will start from here again. So this is our solar system planets, all in true colors. Now, I have to search a lot, because if you go on the internet and just type any planet, you get the image of that planet, which is of different, like if you take Venus, it will be like very like hell, like the structure. But it's not, it's very different. You can see this is Venus. It's so cloudy that it entirely masks what is inside. So if you see the true colors, they are different for different planets. And you can imagine the variety here is so much. Like we were astonished by seeing the variety in our solar system itself, and this has been just recent, and this has been possible because we have been able to reach these planets using spacecraft. So like the Juno reached Jupiter, but Jupiter has been we have been to Jupiter using other spacecraft like Voyager. And then the most recent one has been the New Horizons, which reached Pluto. So all has this been possible because we have been able to reach those planets using spacecrafts. And you might notice that there are 10 planets here, but you might have learned in the literature there are 8 planets. So can you identify which one are those which are not the planets? So one is the Pluto, and one is the Ceres, which have been like, Pluto has been stripped of its name as a planet, so it's a dwarf planet now, and same is the Ceres. And these are the other main planets of our solar system. Now, once we know this planets in the solar system, now I will take you to like when was the first exoplanet discovered. So like we were thinking like we should be able to see the exoplanets. Everyone was trying very hard, but it was only in 1992 that the first exoplanet was discovered, and that was very surprising because that was discovered around a pulsar. So what's a pulsar? Pulsar is a very strong rotating. It's basically a neutron star which rotates very fast. And to find a planet around, everyone was surprised. Like how could a planet survive in such extreme conditions, because pulsars are basically formed when after the supernova stage. So everyone was surprised. If planet could form there, can be found there, it would be possible to find planets around other stars also. So so everyone started rigorously working on finding planets around other stars. And then in 1995, then the first time a planet was found around a main sequence star. So a Jupiter-Mars companion to a solar-type star. This was the first discovery in 1995. So this planet was actually 51 Pegasi, which is around 50 light years away from Earth, and like everyone was like amazed that like we found a planet, and from that time, from 1992 and 1995, this discovery, the revolution began to find exoplanets, and then we have now reached a number of 3,700. You can imagine from that one in just 23 years. You can imagine we have reached that big number. Now, and then to give a perspective of what exactly are we observing here. Like if you look at solar system, then you can see planets very clearly, like what is their color. But in reality, now this is the nearest exoplanet we have ever found. This is just 2 years ago in August 2016, which is Proxima Centauri b, which is the nearest exoplanet ever found. And you can see this structure. This is but an artist impression. This is the real, what the planet looks like, you can see. This is how we find it. So to just bring you to the reality, this is what the real planet is. It's not like this. So why? Because the distances are very, very far here. Like, our mind cannot comprehend those distances. Like this Proxima Centauri is 4.25 light years. You will think it's just 4.25 light years, but that is, the light takes 4 years to reach there. It will take, the fastest thing that we have currently, we can, is the Juno spacecraft, which went to the Jupiter, and for it to reach Proxima Centauri, it will take 3,005 years. You can imagine 3,005 years to reach that. With the current, the New Horizons took 9.5 years to reach Pluto. So you can imagine, like, it's not even possible in our lifetime. So the distances are very, very vast here. So we can't imagine to get the full image of this planet. So what we best do is to get the information if there is a planet and then like analyze them. So this is the first technique. How do we find this planet? So this is how this planet was found, which is the radial velocity technique. So I will take you to now how we do this. So there are many techniques to do that, but the two most successful techniques are, the first is the radial velocity technique, and the second is the transit technique. So in the radial velocity technique, what basically we do is, so you can see this is, suppose your host star, and this is your planet. Now what happens is, now if you are if you know basic gravity, then actually the angular momentum experiment you saw in the second talk by Aaron, you saw a person was like sitting there and when you pulled. So it's not directly connected with that, but each object pulls each other object. So you can see this is, suppose, your star, and this is your planet. So a planet is revolving around the star, but actually the star is also revolving around a planet in a sense, because they both have their own gravity, but the star is very much bigger, so it's not, it looks like it is not moving. Even sun is moving. It has a small orbit around. You can see this, even sun has it, but it's very small to notice. But that can be done using precise measurements. And here, so suppose, so as I showed for Proxima Centauri, you can see that graph of the planet detection. So suppose planet is rotating around a star, then that particular star will have a small revolution around that, and that can be measured using spectrum. So what happens is, like if you are on train station, if you are standing there and a train is coming towards you, then if you hear the sound, then that frequency increases. You can hear the sound like that. Maybe I didn't do it well, but and as it goes away, that frequency decreases. Now this happens with sound. Same principle can be applied to light. Like in the light also, when the suppose the star, here we are getting only the stellar light. We are not getting a planetary light. So when the star is coming towards the Earth, then that particular the entire spectrum will be shifted to will be blue shifted, because blue is higher frequency. Here, this thing blue, and you can notice that actually if you look carefully. And when that star is going away from the Earth, then that will be red shifted. And from this, we'll understand if there's a planet or not based on how much it shifted. And from this we can actually, because here the bigger the planet, the bigger will be the movement of the whole star, and the bigger will be the shift. So from that we can determine how big how massive the planet is, and basically you can find planets. And this is the technique by which the first exoplanet was detected, the 51 Pegasi and even Proxima Centauri. But this has not been the most successful technique. And the reason is because it's very difficult to make this measurement. The most successful technique is this one, the transit method. And it's very simple to understand. It's basically like an eclipse. So basically, if you have a star here, and the planet goes in front of the star, there will be a dip in the brightness of the host star, and basically you have found a planet. So it's so simple. You can do it easily if you have a good telescope to continuously look at a star. And so most of the planets out of 3,700 I mentioned have been detected by this method, transit method, and mainly because of the Kepler spacecraft. And the things that we have achieved, because this is just like astonishing. You can see this is the Kepler orrery in 2012. So orrery means it's all the planets that we have detected up to 2012 and their orbits. So you can see a lot of, the variety here is so much, but you can see a trend also here. Like this is our solar system. So solar system is quite widespread. Like if you take Earth is like 1 AU from the sun, but most of the planets that we have detected are very close to their host star. And do you think what might be the reason for that? The main reason is basically it's easy to do that, because if the planet is very close to its host star, like it's you have to just wait for 3 days to observe that planet, because we have to keep pointing the telescope only for 3 days. But if it's like Earth, which has which 1 year is 365 days, then you have to wait 365 days to observe that planet transit around that. So that's why, and to confirm like if a planet is there, we have to do this at least 3 times. So that's why it's easier to detect planets which are very close by. So actually, so you might notice all the planets that most of them we have detected are very close to their host star. They are so close that even Mercury is to our sun. Like we did not expect that such planets existed, but when the first planet was detected 51 Pegasus, it was very close. So Mercury takes like 88 days to orbit around sun, but generally the exoplanets that we find, the hot Jupiter planets, take around like 3 to 4 days. So basically, if you are on that planet, it will your 1 year will be 3 to 4 days. So you can celebrate your birthdays every 3 to 4 days. But they are too hot for that to live. So now this is the type of the orbits that we have. Now the variety in the size of the planets itself is astonishing. Now the 3,700 planets, now you can see the variety here. Now the most of them we have, as I said, we have found are very giant hot Jupiter planets, which are like Jovian, which is similar to our Jupiter, which are very massive gas giant planets. And then there are some mini terran planets, which are like Mercury size, sub-Terran, which are Mars size, then Earth size. So you can see there is a lot of Earth size planet actually we have found, 701 out of that. And then the sub-Terran. Now this is one of the anomaly. Actually we don't have any analog for this in the solar system. So this is kind of exciting. Like what kind of planets will be this? Like it's a terrestrial planet which is 10 times that of like Earth. So we are like excited. In fact, there was this a small story I heard somewhere, like if there is a Superman, then he would be from this planet, he or she would be from this planet, because this will have higher gravity and still it can exist, the life can exist there. So it's just a story, so I don't know, but this is an anomaly that we don't have any analog in the solar system for this kind of planet. So this is exciting. And then there are planets like Neptune and Jupiter size. There are many of those, but this is just the size. Now, as I said before, they can be at different distances from their host star, so that will determine what temperature they have, and therefore the atmospheric dynamics and everything. Now, once we know what kind of planets we have, now there is one more thing actually. So can you remember this picture? Where is this from? Can you guess? You can shout it, no one is stopping you from that. So Star Wars, yeah. So this is the picture. Which planet is this? Can you remember? Tatooine, yes. So why is everyone? So this is Tatooine, and you can see there are, like, if you see Tatooine, there is like two suns on that. It was shown. So actually, just recently, when the Kepler spacecraft, we actually found a real planet which is having two stars. Means it orbits 2 stars. Basically, it has 2. If you go on that planet, you will have 2 sunrise and 2 sunset. It's called Kepler 16b. So basically, which was something that was science fiction like 20 to 30 years ago. Now it's becoming a science reality as we go ahead. So that itself is interesting. Now let's come back to the science. So once we have found a planet, the most important thing now, if we want to detect life or biosignatures there, is to study its atmosphere, because all the signature of the atmosphere of the life will be in planet's atmosphere. So this is how we do it, and this is actually what the Exeter University we specialize in, and I and our supervisors work in. So what we do is we actually use Hubble Space Telescope, as you must have heard. Like, it's the most powerful telescope in space currently. This is it. It looks like this, and this is just an again to bring you to the ground. This is actually what it looks like. So this is actually a planet WASP 39b. When it went in front of its host star, it actually looks like this. This is the image from the Hubble Space Telescope, and then we have to do a lot of processing to understand that planet signal and what's in its atmosphere. So I will take you to the basics of how we do that. So suppose this is your host star. and this is your planet. Now what will happen is some of the light from the star will also go through the planet's atmosphere here. You can see there is a planet atmosphere which goes above your land or whatever is there beneath. So some of the light will go through here. Now what we do is we capture this light using telescopes on Earth. So you can imagine telescopes are basically like a prism. So which separates light into different colors, like a rainbow. So if you have a prism, you can separate lights in different colors, and you can see different colors of light, like a rainbow, and you make like a spectrum like this. You can see different colors from blue to red. Now from basic physics, we know one thing, that different gases absorb different colors of light. Like oxygen absorbs red color of light, while sodium will absorb yellow color of light. So from that knowledge, we can actually determine which particular gas is present in that atmosphere, because if suppose sodium is present in that atmosphere, it will absorb yellow color of light, and that color of light will be missing in the spectrum. So you can see here the two black lines here are basically because sodium is present in that planet and it is missing from the spectrum that we see. So basically you have found a sodium in the atmosphere of that planet. So in this way we can actually find which different gases are present in the atmosphere. Now, so actually, how we do it is we actually we can just measure the radius of the planet, and this is like, so the radius of the planet will be different in different wavelengths or different colors depending on which gas is present in the atmosphere. So suppose in this color, planet will look smaller because that particular gas is like it will look smaller because that particular gas is transparent in that color, while in this it will look bigger. So from that we can determine which gas is present in the atmosphere, as I explained before. And then we come to make a graph like this. So this is actually for a real planet called HD 209-458b, which is around 159 light years away from us. And what here we are showing is this is the wavelength, which you can imagine is basically like different colors of light. And this is like radius of the planet divided by the radius of star in these different colors. And this is what the real observations look like. So this is the real observation after processing from Hubble Space Telescope for this planet, which is like a sun-like star with 3.5 day orbit, as I mentioned, and a temperature of around 1200 Kelvin. So basically around, yes, I forgot how to convert into degrees Celsius. So now we have these observations. Now what we do next is, now we need to understand what these observations mean. So there we come in. This is what we do is we use an atmospheric model, and this is like what I do. So in this, basically an atmospheric model is you have to understand the entire atmosphere and represent them in terms of equations and put them into supercomputer to solve it. So basically it will have all the things that nature has in it, like clouds, lightning, volcanoes, if there are aliens, what they're emitting, cows and everything. You really want everything to be represented in it. But it's very difficult to imitate nature. So we start with simple things. So the first simple thing is radiation. We start with that. We use like the radiation from the star coming in the planet. How will it heat the atmosphere? How will be the weather? All those things. We include first that. Then we go to clouds and all these things. So we try to do our best. We convert them into write them in terms of equations, and there are big models. So the best example for this is the UK Met Office model. It's 10 million lines of code that solves for the Earth's atmosphere and give you weather prediction. So basically we are doing the same for other planets. But here, for Earth, we have many constraints because we know we can measure. But for exoplanets, we can't do that. So we start with some assumptions and go ahead with that. And then observations guide us, and we change those assumptions. And then we use massive computers to solve them. And then this is what we get basically then. So this was the observations before, the blue points. And then this is the continuous line is the model. So you fit your data to the model and you get finally what is actually in its atmosphere. So this is for that real HD 209 planet, and this is all what we have found on that planet. Now the first important thing we have found is Rayleigh scattering. Now what does it mean is when you go outside and look at the sky when it's blue, now the blue color of the sky is basically due to this process called Rayleigh scattering. It is basically due to the small oxygen and all the gases present in the atmosphere. So actually we have detected this process on other planets. So it might not be blue color, but it has a dependency. It might be some other color depending on what is there in that planet, but it will have this process called Rayleigh scattering. Then the other important thing, we have actually found sodium on that planet. So that's why it's yellow color. So you can see there's a peak here. So it means that the planet looks bigger in that color, in yellow color, because sodium is present and sodium absorbs that light, and that's why it looks bigger. So we have found sodium on that planet. We have found potassium on that planet, which is in the red color. And everyone's favorite, we have also found water on that planet. Now you might be surprised, like, how we found water on that planet. Isn't that amazing? But the problem is this water is actually in liquid, not in liquid state. It's in water vapor state, because as I said earlier, this planet is at very high temperature. So that's why the water there cannot be in liquid form, but it's in the vapor state, and we have detected this water peak. And here I haven't put any color because this is actually in the infrared. So our eyes cannot see that, but but using instruments we can see that. And this is one of the peak absorption bands of water at 1.4 microns. So, and you may be surprised at how common the water is. Actually, we have done a big survey of like around 10 planets, and in most of them we have actually seen water. Around like 3 to 4 planets we have seen water. So it's very common actually to form water. It's one of the most common like molecules that we see in the universe. Then, so this is actually my work. So we have actually created a big public library of models of like 117 planets. I shouldn't say my work, our work. So basically all my supervisors and everything, we did that. And so this library can be used to interpret the observations of any of the planets. That you can start, like only 10 or 15 have been observed. So there are more to be observed and studied. And recently there was in news, actually, we actually detected sodium and helium in 2 of the atmosphere. It was just in just this month, this news was all around. Now, once we know like what are the gases in that planet's atmosphere, we need to now the bigger question, that is it suitable for life? Now that is an obvious question that will come into your mind. So now for that we need to first understand what are the requirements of life. Now, the 3 fundamental requirements of life are, like, the first is the energy source to drive metabolic reactions. So in our case, that is the sun. That gives us all like the energy for driving the metabolic reactions. Then the second most important thing is the liquid solvent to mediate this reaction, so that when the reactions happen, there is some solvent to do that, and that is water in our case. So you have sun, water, and the third is a suite of nutrients to build biomass. So in our case, those are the trees. Basically, all the things that we eat or the animals eat, they basically come from trees or plants, because they are the actual thing which are converting the sun's energy into biomass using and converting into carbon molecules or the things that we can eat basically. So these are the 3 requirements that you need for life. Now, so you need to understand what can be the biosignatures using these 3 requirements. Now, if we just look at our solar system, these are the planets we have, and you can see a clear exception, which is the Earth. It's only Earth that have oxygen in it, while other planets, like, it's mostly like, if you go to Venus, it's mainly CO2. If you go to Mars, it's mainly CO2 because they are terrestrial planets. If you go to like gas giants, they are mainly hydrogen and helium. There is a Titan, which has methane in it. So everyone was very excited when we found Titan, but it's very, very cold to have. Like, I will come back to that. Like, it's called Habitable Zone. So Titan is an interesting planet, but it's very cold for that. So as of now, we have only one planet where we know life exists, and that is Earth. And oxygen is one of the the things that differentiate us from other planets. So you can say that oxygen is a biosignature. And then if you go in a bit more details, like this is a spectrum this is for Mars, this is for Venus, and this is for Earth. And here also you can see CO2 is there in all of them. So you can't say CO2 is a biosignature because it's in all of them. But there is one signature here of ozone. So you can say ozone is a biosignature then. So you have oxygen and ozone that can be that are biosignatures. But is it true? So previous thought was detect oxygen and get a Nobel Prize. Everyone used to think like that. But now the current thinking is it is more complicated than that. And I will tell you why. Why is that? So first is oxygen. Now, now if you're finding oxygen, now there are, as a biosignature, there are many the most important biological source is basically your leaves. So from that you get sunlight, you take carbon dioxide, water, and form glucose, which we eat, and leave oxygen. And this is like the primary source of oxygen on Earth, sorry. But there is also a non-biological source of oxygen, which is basically due to dissociation of water due to UV radiation. So this can happen on other planet, and basically you can form oxygen using this. So you can't definitely say that oxygen is a biosignature. We think like that. It might be there, it might not be not. There is like ambiguity to that. Then ozone. Now for ozone, so basically ozone is a product of oxygen. If you have oxygen, then only you will form ozone, and that is because of the sun's UV rays. You have ozone, you split that and you form, if you have oxygen, you split that and form ozone. And the non-biological sources of ozone will also be same as that of oxygen. Now we go to methane. Now, methane is a biological source. You get it from like cows and all the animals around that. This is an exaggerated picture. It doesn't happen like that. So the methane has a biological source, but then there is also a non-biological source for methane, which is like geothermal. So if you go to like Iceland or like some places in the Himalayas, you can see there are geothermal springs which take the methane from the bottom of the atmosphere. Even on Mars, we have found methane which they think is mostly geothermal, but we are not sure about that. But there can be a non-biological source. So methane we can't say for sure that it's a biological signature. Then there are actually two compounds which like go which we don't know much. So I read a paper recently, and there I found about this, which is like a DMS. It's called dimethyl sulfide. So here I'm showing the biological source, which is like a cabbage. So if you cook your cabbage at home, the smell that comes, that is basically dimethyl sulfide. So it's a good biological source, and we haven't found any non-biological source for that. So this can be a good biosignature for detecting that, but it might be difficult because it's also depending on how much concentration is there in that atmosphere. And there is one more, which is chloromethane, which is basically due to algae that you have in the oceans and everywhere. That is also mainly due to biological, so that has biological source, but we don't have any non-biological source for this particular chloromethane. So we have two molecules actually which can be used. But the problem here is how much is the amount of this in that atmosphere, and is our current technology capable to do that? So all these questions have to be kept into mind. And then the other important thing is it's just not the like where the planet is, or it's not just like what biosignatures are. We need to determine if the planet is at a suitable location for a life to evolve. So there the term habitable zone comes into picture. So like this is suppose a star, and these are different locations of the planets. Then it has to be in the perfect place. Like we are lucky that we are in the perfect place, we would say. Like it's not too hot, it's not too cold, it's just right for the water to stay liquid on Earth. So this all things has to be taken into account. Means the water should be in the liquid state, the wind should not be too high. All these factors have to be combined together for life to sustain and evolve. It's not just like life should just form there, it should evolve also, and it takes millions of years. So this has to be maintained for millions of years. So it's a very difficult process. So you can see how difficult and how rare it is to form life. You can appreciate that from this. Now I went through the process of how we study exoplanets, what's the life, and like just to complete and wrap up, I will just take what is the near future. So in this case, now the most of the planets that we have detected, 3,700, we are using the Kepler spacecraft. And in this, suppose this is our solar system, the sun is here. We just scanned this part of the sky. You can see the Milky Way is so big. We just scanned this part of it, around like 3,000 light years. Only in this region, we found like more than 3,700 exoplanets in just this part of the sky. So you can imagine how many planets will be there just in the Milky Way. And there are like many galaxies are all around. So, so just give an example, like she mentioned about stellarium. This is from the stellarium. So this is the Kepler field of view. If you open stellarium and see, so if you go at night, if you see Vega, Altair, and Deneb, which is the summer triangle, so you can see all the planets that we have, most of the planets that we have detected are in between this summer triangle, because this is the Kepler field of view. So the Kepler spacecraft is looking at this part of the sky, and most of the planets we have detected are here. So just to give you an inspiration, you can do that. So now what is the future? Just last month, this satellite was launched, which is actually the Transiting Exoplanet Survey satellite. So this is how actually it is going to scan the sky. So you can see it's actually doing a full sky survey. Kepler was just looking at one part of the sky, but this is actually, first it's going to scan the southern hemisphere, then the northern hemisphere. So it will try to cover all possible part of the sky. So you'll get a bigger sample spread around the like our galaxy for different kinds of exoplanets. So it's very amazing that we can do that using, and it's just launched last month. So there are many like new results in like 1 year. You can expect many different kind of planets and exciting results actually. And then, of course, everyone is waiting for this telescope for last 10 years. Now, this will be like the beacon everyone is hoping for, like, because the Hubble Space Telescope is currently the biggest, and this is going to be the biggest ever once this is launched. I don't know when that will happen. So once the plan here is, first the test will find planets, and then JWST will go up, and then we'll use this to characterize those planets. So in the same step, find planets, then study its atmosphere. So this will be actually used to study its atmosphere. And the benefit of using this telescope is it's actually works in quite of infrared range. It goes up to large infrared wavelengths, which is like up to 20 microns, so that we can image quite a lot of Earth-like planets there. But it's difficult, we know, even with this telescope, but we are still attempting that, basically. So there are many exciting results to be found, and thank you very much for listening.